So today we are starting the discussion of analysis methods for dynamic circuits, and we have already seen the state equation. This will be the analysis methods other than the state equation. So what do I mean by that? We will be studying mesh analysis, node analysis, and modified node analysis. So this will be the example that we will be studying. Well, if we check this circuit, there is a mutual inductor and a capacitor and a single resistor. Now, previously we have studied how to formulate this in terms of state variables. So what are the state variables for this circuit? If we draw, for example, mentally the graph of this circuit, there is a branch like this. Let me put this branch on the tree. There is another branch like that. Let me put that branch on the tree. And then we are left with three other branches. I need to reach this node. So I'm selecting this branch and putting it on the tree. So my three branches are like this. And then my state variables will be in this circuit. Voltages of the capacitors on the tree. So what was my tree? It was this. And currents of the inductors on the co-tree. So which are I1, I2. So this tells us that my state vector for the state formulation is a 3×1 vector. Okay. So if I write the state equation system, let's review. Then I have this 3×3 A matrix, and I have a single source, which is what we call input also. I have a state equation like that. Again, this is a first order matrix differential equation. Now, we have studied the homogeneous solution and the particular solution of the state equation. So how was this, if we remember? So this is, let's say, the complete solution. Okay. Now the homogeneous solution is something like this. I have K1, E1, e to the lambda 1t, plus K2, E2, e to the lambda 2t, K3, E3, e to the lambda 3t. So actually this is the homogeneous solution. Okay. So what are these? K1, K2, K3. These are undetermined coefficients, okay, of the homogeneous solution. So what are these lambdas? Lambda k, ek are the eigenvalue and eigenvector of this A matrix. Okay. So we have spent considerable amount of time how to find this A matrix and then how to write the state equation, why this is true, etc. and etc. For example, if we have no input, then this homogeneous solution, okay, homogeneous solution, let me erase, I have already written it, plus 0 will be the complete solution, because if you have no input, then the particular solution is equal to 0, then this becomes the complete solution. I just need to satisfy the initial conditions by properly selecting K1, K2, K3 values. Okay. So again, we have discussed this. Now, if the input is, let's say, the particular solution. If the input is, we have studied this thing in this form, e to the s naught t. And this s naught value is not equal to one of these lambdas. So what are these lambdas? They are called the natural frequencies of the circuit. So S naught is different from the natural frequencies of the circuit. So what is this part? Well, again, we have studied this a little bit. S naught minus A inverse B e to the S naught t. Okay. So S naught is this S naught, and so on. So for this eigenvalue calculation, so let's remember, lambda I minus A, lambda k, let's say, times Ek is equal to the 0 vector. Okay. So this lambda k, Ek satisfies this equation, so there are some specific lambda values for which this ek becomes a non-zero vector or a non-trivial vector, and that vector will be called the eigenvector of this A because of this formulation. So as you see, if S naught is not equal to lambda k, so then this equation is clearly this matrix is different from this matrix. And if it is not equal to it, this matrix becomes invertible. And if you take the inverse of this matrix, do that calculation, we get the particular solution. So this becomes, as I have said, the complete solution for the state equation system. So, but now, this is just to remember what is going on. I would like to apply my mesh analysis knowledge for the formulation of this circuit. Okay. So how can I do that? Actually, this is an earlier topic that we have seen in 201. This is a classical circuit analysis topic, mesh analysis. So how can I write the formulation equations with the mesh analysis? So the thing is, I should first introduce these mesh currents. Let me call this mesh current capital, let me use capital letters, Ix, mesh current Iy, okay? Then I will write KVL equations in, let's say, mesh X and mesh Y. So let me write it like that, KVL around mesh X. Okay, I think X is this one. So how can I handle this? Now I can handle this by just, I'm traveling in this direction, in the Ix direction, minus Vx of t plus V1 of t plus V2 of t is equal to 0. So what is V1 and V2? Let me introduce them. So this is a mutual inductor. Okay. So as you see, I1 enters into the dot, and there's a plus sign aligned with the dot. I2 enters into the dot, and there's a plus sign enter next to this dot. Okay. So with this assignment of polarities and the currents, then I know that this mutual inductor will be represented with these equations. Okay. Again, this is the convention, what we call the passive sign convention for the mutual inductor. So which one is the first one? The first one is 2 Henry, 7 Henry, mutual inductance is 3 Henrys, and so on. So this dot obviously refers to differentiation. So I have the following I-V relationship for the vector components. Okay, you take the derivative of this vector, multiply by this L matrix, and you get the voltage vector. That is it. So again, if this 3 is equal to 0, I have uncoupled two inductors. Uncoupled inductor number 1, uncoupled inductor number 2 with 2 Henrys and 7 Henrys, if this off-diagonal term is equal to 0. That's the simplest case. But in practice, there is always some coupling because of the electromagnetic fields and its propagation and so on. There is some amount of coupling between the inductors. It's unavoidable, but sometimes you can neglect that. Okay. So let's go back to this. Now, mesh analysis, and I need V1 plus V2, which is good. But if I write V1 plus V2, what do I have over here? Well, I have, add these two equations. If you wish, you can add them like this. Okay. Or you can multiply them by 1, 1 vector from left. Okay. This is more technical actually. If you multiply by 1, 1 vector from left, over here you have V1 plus V2. But let's erase this. Let's do not unnecessarily crowd the whiteboard. So if I multiply it, I have 5 and 10. So 5 I1 dot plus 10 I2 dot of t. Okay, V1 plus V2. I get V1 plus V2, which is good. But what is the goal of mesh analysis? So the goal of mesh analysis, let's repeat this, writing equations involving only mesh currents. What are the mesh currents? Ix, we see, and Iy as unknowns. Ix of t, Iy of t as unknowns. Okay, so I need to see, if I'm doing mesh analysis, Ix and Iy in my equations. So this is my first equations, and I see not Ix, Iy, but I1, I2. Now, the idea of mesh analysis is extremely simple. If you know this branch currents, if you know this mesh currents, Ix and Iy, okay, these branch currents are simply a linear combination of the mesh currents. This is the big idea of mesh analysis. As we have discussed, this is only valid for planar circuits, but whatever. So I1 is equal to Ix. So if you wish, I can also write it over here. This I1 is equal to Ix, because this is the only branch passing from here. How about I2? I2 is equal to, going down, it is Ix minus Iy. If I take the dot of them, I will be putting a dot on top. Okay? So then this becomes, okay, let's do this. Ix is equal to, I1 is equal to Ix of t. I2 is equal to Ix minus Iy. And then, what do I get? I get 5ix plus 10ix, 15xt, and done with this, minus 10 Iy of t. Okay? I think that is it. So this would be our equation. So if I write this 15 Ix of t minus 10 Iy of t derivative is equal to then Vs of t. Okay, this will be our equation number 1. Okay, so it's not very complicated, as you see. The idea of mesh analysis, you introduce mesh currents and then you write KVLs. In the KVL equations you are writing voltages. Express these voltages using component laws in terms of mesh currents. In other words, express the branch current in terms of mesh currents and use this component law to write the voltages. It's very systematic and quite easy. Okay, now let's do KVL around mesh Y. So let me write this, minus V2 plus 1 times Iy, okay, and then I should be writing this thing, Vc of t, voltage of it, right? Vc of t. So how about V2? I know how to handle V2. Okay, we have studied this. Well, let me write this, minus V2 then is equal to this line. Okay, so this is, well, 3 plus 10ix dot minus 7iy dot. So this is 7iy dot, because of this minus 10ix dot. Okay. Let's check. 3 plus 7 in terms of ix, I have 10ix dot minus 7iy dot. Okay. Which one is 10ix dot minus 7iy dot? Okay. So we are done with this. So why am I saying we are done with this? So this is supposed to be mesh analysis. So I need my unknowns, only mesh currents. So these are the mesh currents. I am done. This is also mesh current. I am done. How about this? This is not a mesh current, obviously. So how do I write this in terms of, currents? So we use the terminal equation for the capacitor. Am I right? IC of tau d tau. And this is valid after the initial condition, which I want, because I'm analyzing this circuit after the initial condition. So this equation is what I need. Okay. So here you see IC, but I don't want to see IC. I want to use either Ix or Iy. But I see as simply Iy. Okay? So this is Iy. So in this equation, 1 over c is 2 over 3 then. This is equal to 2 over 3. Okay. So if I write my second equation then, my second equation is minus 7. Let me write it, sorry, plus 7 diy, let's use d notation, minus 10 dix plus iy plus v naught, so this is plus 2 over 3, and I would like to use d inverse notation, d inverse iy. So this is equal to 0. This is my second equation. Okay. So this is the end. So I have written two equations. You may say two unknowns, ix and iy, but this is a differential equation. So let's try to write this a little bit more carefully then. So let me use this part. Let's use, matrices for the compact writing of this equation system. So my unknowns, ix of t, iy of t. So the known quantities are always on the right hand side. For example, over here, I have vs of t, 1, 0. Well, I don't know whether this is 0, 1 vs of t. Okay, so 15 ix dot, so let me separate this, 15d, okay, minus 10 diy is equal to vs of t. So clearly, first row of this matrix represents my equation number 1. Okay. Now the second row. What is the coefficient of ix? I see only one ix. This is this. What is the coefficient of iy? 7d plus this plus this. 7d plus 1, this is 1, plus 2 over 3, d inverse, so the whole thing. Okay. And then I have handled iy, so I'm left with this thing. So my second equation is done. How many terms do I have? 1, 2, 3, 4, 5. I think I'm done. Okay. So I can erase these equations. And let's see. Have we written everything correctly? 15d. Okay, it seems right. So let's erase these equations, and then that will be the end of the circuit formulation, but you should be a little bit careful. Now you can say that, well, in the state equation system, these quantities, state equation representation, the initial conditions given were also the initial conditions of the state equation representation. So how about this one, ix and iy? Well, no one tells me what is ix0 minus, iy0 minus, and so on. Okay. So if this is a differential equation, then I need to have this initial conditions also. But before that, maybe we should notice that. So there is d inverse operator. Okay. So because of it, this is called an integral differential equation. So let me write star. Star is an integral, that is integral and differential. Differential equation system. Okay. So it's a 2 by 2. There's a matrix over here. But is it a first order differential? Well, it's not a differential. It's an integral differential equation. But indeed, the derivative term is appearing only with the first order. Okay. So that means that if I need to solve this, I need to have the initial condition for ix, iy, because d is operating on iy, ix, iy, that is it. So I need to have for the solution of this, because as I have said, differential operator operates on this and operates on that also. So initial conditions for just a node, ix 0 minus, and Iy0 minus are required for the solution. Sorry, initial conditions for the solution. So how can I find them? Well, you can do the following if you wish. If you wish, you can also, target the 0 plus initial conditions. So, well, let me do the 0 plus initial conditions, doesn't matter. So I will be looking at t is equal to 0 plus circuit. Okay. Now I have this at 0 plus, a specific time. Assume there is no impulse. Okay, we are looking at an easy case. If there is impulse, it's not a big deal. We can always handle impulses. We know how to handle impulses, but right now, these are mutual inductors. There is no impulse, and then that means that inductor currents are continuous because energy variable is continuous. So what do I mean by this? Well, there is this I1, I2, 0 plus values. Am I right? So I know those values because they will be equal to the initial condition. So let me make it very visual by a current source. I1 0 plus is equal to I1 0 minus. Hence this is I1. Okay, current source I1 because I'm looking at the 0 plus time. This is equal to I2 because I2 0 plus by the continuity of the inductor current in the absence of impulses. So this is I2 0 plus. So what was my mesh current then? My mesh current was, let me use this, same color. So this is Ix at 0 plus. This is Iy at 0 plus. Why I have switched to 0 plus? Because these equations are valid for 0 plus, so it's a good idea that we switch to 0 plus. So from here, Ix 0 plus is again mesh current is equal to the branch current I1. This is this current source. Iy 0 plus is, so this is Iy 0 plus. So this current going down is I2. So, or you can do it this way. I1 minus I2 is this current. Okay, that's easier. I1 minus I2 is Iy 0 plus. Because I have current sources right now. I1, I2, I1 minus I2 should be there, and this is this. Well, let's check. So this mesh current minus this mesh current should be giving me I2. This is the first one, minus, yes, it is correct. So here are the initial conditions then for mesh analysis equation system. Okay. Very nice. So I was able to express, the initial conditions also. I can go ahead and solve this. Now, what is the solution and how can I handle the solution of this type of differential equation? So, let's erase this. So this is an integral differential equation. So again, I want to erase this one also. Again, this is a constant coefficient differential and integral differential equation. Okay. So how should I solve this? Again, there is this homogeneous solution issue. Homogeneous solution. Okay. So how do I handle the homogeneous solution? So I will be making a guess. Well, should I say this? AB, okay. E to the lambda t. This is for the homogeneous solution. So when we talk about homogeneous solutions, we take the input is equal to 0. Vs of t is equal to 0. Because this is the term appearing on the right hand side. But specifically for this formulation, we see that V0, the initial condition for this capacitor, is also appearing, so you may say this is the forcing term. So this is a vector, okay, forcing term, whatever you have on the right hand side. So this is also acting like as, you know, as in power or in principle, almost like an input, isn't it? Because this is appearing on the right hand side like a constant term, like a DC source is the input of this, it's something like that. So for the homogeneous solution, again, you'll be assuming that since this is an integral differential equation, we have this term, we'll be assuming that right hand side is equal to 0. That is, this is equal to 0, this is equal to 0, so right hand side is equal to 0. So if that is the case, I'm making a guess like this. And what is the procedure? Insert into equation. What was this? Insert into star. Okay, let me write a little better. Insert into star and try to find a solution. Try to, you know, we don't know this value. Sorry. We don't know this value. We don't know this value. We don't know these three values. I'm trying to find, you know, a solution for A, B, and natural frequency. Okay. Then, if I substitute this, well, the issue is the following. Let me call this, well, if you take the derivative of this one more time, you have, we have discussed it several times before, lambda coming down, let's say, as the coefficient of a multiplier of this AB vector, isn't it, if we take the derivative. So this is the main thing with differentiation and exponential functions. So the exponent comes down and multiplies these coefficients. So if I do that, if I do this substitution, you will see that I need to multiply this by 15 derivative, 15 times 15d. So that means that I'll be having 15a times this lambda at the end. So if I write this matrix, let me write it this way. If I call this an M matrix, which contains a D derivative operator, okay? So I'm doing this, M matrix with D, and I'm multiplying by AB, e to the lambda t. This is equal to 0, 0. Okay, because right hand side is assumed to be 0 for the homogeneous case, as we have discussed. Now, this is nothing. I haven't done the substitution. This part is the homogeneous guess for our homogeneous solution. So if you check this, then if you do this operation, you have m lambda AB e to the lambda t is equal to 0. In other words, wherever you see a derivative operator, you are substituting by lambda, because specific for this exponential function, this exponential function is present over here and present over there. A e to the lambda t, b e to the lambda t. So whenever they interact with d operator, you get a coefficient of lambda. So there is d inverse. This is the inverse operation. This time you are deleting this lambda factor by dividing by lambda. Okay? So this can be very concisely written. If I have defined this, m of d, this becomes m of lambda, and this is again supposed to be valid for all t greater than 0. Then I can cancel this. So I'm looking for the following. 15 minus 10 minus 10. So I'm replacing, as you see, let me write 1 over lambda, more visible, this. And I'm looking for the solution of this equation system. So after this cancellation, again this becomes time independent. There is no t in this equation. So is this clear? Over here, instead of d, I'm writing lambda. So this is that thing, something very simple. So what's the solution of this? You can say this is a and b is equal to 0 is the solution, which is correct. If you put 0, 0, whatever lambda is, you get the solution. Okay, equation is satisfied. But that is not a very interesting solution, because you know this 0 vector obviously satisfies this homogeneous equation. So for a non-trivial solution, then this matrix, again m lambda determinant, has to be equal to 0. Am I right? For a non-trivial solution. Okay. So how can I handle this? Then I can express this derivative, 15 lambda times this. This was 7 lambda plus 1, 2 over 3 lambda, and I have minus 100 lambda square is equal to 0. Okay. So if I do this, what do I get? So I need again more space, but let's erase this a little. For this calculation, let's go over here. Okay. So this is 105 lambda square minus 105 lambda square. So I'm going like this, 5 lambda square. So down, I've gone down and I'm over here, 5 lambda square. So what is the constant? Now I have 7 lambda over here. No, I have 15 lambda over here. And what else? Oh, I'm left with this term. 30 divided by 3, 10 is equal to 0. Okay. So this is again a quadratic, or it's a polynomial. Okay. And then if I divide by 5, lambda square plus 3 lambda is equal to 0. So I get my natural frequencies as this. Okay, natural frequencies as this. So is this the end? It's almost the end. So if natural frequency is, for example, minus 1, then how can I find this AB vector? Well, you insert minus 1 over here. So let me do this. Do I have enough space? Perhaps. If lambda is equal to minus 1, okay, then I have minus 15. So I'm writing this equation right now. M lambda AB is equal to 0, 0, but lambda is equal to minus 1. Okay. So I know that this has to have a non-trivial solution because right now determinant is equal to 0. So if I do this, so this time I have found the natural frequency number 1 as minus 1. So minus 15 plus 10. This is 10. And this is equal to, well, this is a little tricky. This is minus 6 plus 2 over 3. So this is 6 minus 6 minus 2 over 3. Am I right? Okay. So minus 20 over 3 then. So let's erase this. Minus 20 over 3. Now, of course, A is equal to 0, B is equal to 0. Again, the trivial solution satisfies this equation. But how about this? A is equal to 2, B is equal to 3. It also satisfies this right now. Okay. So when lambda is equal to minus 1, 2, 3 vector satisfies this. 2, this becomes 33, 2, 3, as you see, it satisfies this. So as you see again, we get a non-trivial solution of this. And then we can find AB values also, and we can write the solution as before. So let's erase this part. Then Ix homogeneous, Iy homogeneous, T is equal to, let me write this at least, isn't it? 2, it was 2, 3. 2, 3, K1 e to the minus 1t. Okay? So again, K1 is similar as in the state equation system. So this undetermined coefficient. Okay. So similarly, there will be another vector k2, I'm not calculating that vector, e to the minus t, and do you think that is it? Well, do you remember at the beginning of this discussion, we were saying that, you know, this is a third order circuit, and indeed I have 3 initial conditions, isn't it? So, but I'm only observing 2 over here, because I was able to find only 2 natural frequencies, because I was able to see a non-trivial solution possibility only for lambda is equal to -1 and lambda is equal to -2. So what is wrong? So is the state equation representation wrong? The order of the circuit is 3 is wrong, or this one is wrong? Well, the issue is the following. Well, there is another natural frequency, but it's not visible. So can you guess what it is? Well, because of this term, because of this D inverse term, I'm not allowed to use lambda is equal to 0, isn't it? Because when lambda is equal to 0, you know, this term becomes undefined. So there is a possibility, I will explain this more clearly later on, that for a third natural frequency to be present. And that third natural frequency, we are not sure about it right now. Okay? Is it equal to 0? Well, at the beginning, by the visual inspection of this circuit, we have said that this is a third order circuit, so we are actually sure about it. There should be a third natural frequency. So in mesh analysis, due to the presence of D inverse operators and related with 1 over lambdas over here, and then you are not allowed to insert, because of this calculation as you see, lambda is equal to 0. You can never find this 0 natural frequency because of this 1 over lambda's presence over here. So if you do the mesh analysis, you get all natural frequencies which are non-zero. Okay? So you are getting the non-zero natural frequencies, but you may not observe the natural frequencies at 0. You should be careful in mesh analysis, similarly in node analysis. There can be some natural frequency lost in your system, in your analysis. So how do I decide on this? Well, again, I check the order of this circuit. So one other way of checking the order of the circuit is, assume 0 input case. Okay? So then, can you set this initial condition like 5 amperes? I can set this one as 4 amperes. Then there will be 1 ampere going this way. Okay, this is equal to 0. Okay, I'm just talking about the initial conditions. 5, 4, 1. This is 50 volts, whatever it is. So you see that I can set these 3 quantities in any way that I like. Okay. So you have 3 degrees of freedom. So I have selected them 5, 4, and 30. Okay. So you can select them in any way that you like. So this tells us that this is a third order circuit. So there should be, you know, 3 modes as you see. But I was capable of finding only 2 of them because of this 1 over lambda term present somewhere. Well, that is it. We should be a little bit careful. So let me write it as a sentence. In, let's say, mesh, also in node analysis, we get all non-zero natural frequencies but we may not observe the natural frequencies, the natural frequency at lambda is equal to 0 if it is present. So it may not be there. Of course, you don't, I mean, this lambda is equal to 0. It's not the natural frequency of every circuit. In this case, it is the natural frequency of this circuit. So it's indeed a true natural frequency, and it's not observed because, again, because of this 1 over lambda terms. This is essentially due to 1 over lambda or D inverse terms. Okay. Appearing in the formulation, in the integral differential equation. Integral differential equation. So clearly, when I call it integral differential, there is a d inverse. That leads to 1 over lambda, so I cannot see whether there is a natural frequency at lambda is equal to 0 or not. So in this circuit, what is going on? Why do we have lambda is equal to 0 natural frequency? Well, you can see maybe the following. Again, check the zero input circuit when this is equal to 0. So this 1 ohm and this capacitor sees essentially, forget about this source as I have said, an inductor over there. Okay? They see a single inductor because these two components are sensing the outside world from their own terminals. And they are sensing through this IV relationship across their own terminals. And they can never understand whether there is a mutual inductor or a single inductor in this equivalent part in the left-hand side. Okay? So for the sake of these two, these ones are sensing something like a second order circuit. There is an inductor and a capacitor, so it's a second order circuit. But this left-hand side it can be more complicated. Okay? As you see, for example, there is a possibility of having a constant current over here. For example, this initial condition is 1, this is also 1. Okay? So both initial conditions are equal to 1. This is equal to 0. Okay? So how about this? If the initial condition is equal to 1, this is equal to 0, the voltage across this one, I'm just saying that there is 1 ampere circulating over here and this is 0. Okay, 1 ampere circulating in this Ix is equal to 1 ampere. So if this is equal to 1 ampere constant, its derivative over here, okay? So this is 1, this is 1, they are also constant. So what we see is that V1, V2, constant's derivative is constant. So all the voltages are equal to 0, but you see 1 ampere is circulating over here. Or I1 is equal to 1 ampere, I2 is equal to 1 ampere, and you see that it's a possibility. Okay? So indeed this is the case. But this is not extracted. That bit of information is not extracted from the equations. So how do we decide on this? Well, this is the reason that we use state equations. I don't want to think deeply for every circuit, because state equations, I just calculate the eigenvalues and I get the full set. Okay? But for these ones, if you have to, just be careful, check the order of the circuit. If the order of the circuit doesn't match the natural frequencies that you have found, okay, just be careful. There can be a missing natural frequency, but you are lucky, you know that its value, missing natural frequency, it is, if it is present indeed, will be having the value of 0. Okay? So we know the value of the missing frequency, but we don't know in general whether it is present or not. Again, it's all related with this integration operator. There are further details, of course, but I mean, this is good enough for the solution of this system. So homogeneous part is found. How about the particular? Well, nothing new. For the particular part, particular solution, so, of course, to the exponential input. So I'm assuming that Vs of t is equal to e to the s naught t. Okay. So, what should I do? Well, let me write it briefly. Now I'll be assuming this. This is md, and then I'll be making a guess for my particular solution. Let me call the CD e to the s naught t. Again, s naught shouldn't be a natural frequency because, you will see my guess won't be correct for the natural. I mean, if this is a natural frequency, I know this is the homogeneous solution, so it shouldn't be for this method to work. S naught shouldn't be a natural frequency. So MD times my guess is equal to 0,1 e to the s naught t. Okay, I have something like this. And of course we have this term also, but let's focus on this one, e to the s naught t. So how do you find this? Well, this becomes m s naught cd e to the s naught t, 0, 1, e to the s naught t. Again, the same story happens. So there's cancellation. You make it time independent. And then you take the inverse of this matrix. How do you know that this is invertible? Well, S naught is not a natural frequency. So only the frequencies, natural frequencies making that matrix non-invertible, okay, are given as -1, -2, and there's also a third one, 0. That's the third natural frequency. So this matrix is invertible for this S naught value. Move it to the other side, and then you are done. And of course, you have to be a little bit careful because you have this term and so on, but general principle applies all the time. So you don't need to worry about this. One tactic is, if you want to get rid of this V naught term, you can take the derivative of the second equation. If you take the derivative of the second equation, okay, then this V naught will disappear. So this will be -10d square, d double dot, okay, 7d square plus d plus 2 over 3, okay, ix, iy, 0, and I have this. Now if you have that, this term vanishes, and then you again take the inverse of this matrix and do the operations. But there can be many special cases that you have to take care of, and we don't focus on the solution of this circuits in such detail. Our focus will be state equation system. Okay, so this is just illustration of other analysis methods and how it goes. Well, how it goes is very much in parallel with the state equation system, because this is our solution technique for, constant coefficient differential equations. Now let's do the same thing for, as you can imagine, node analysis. Again, as I have said, our focus is on the state equation system because it is simple enough and it's also very general. So, but still, let's see, what can I do with node analysis? So what is the purpose of node analysis? Well, the purpose is, let's again write in black color. So writing, let's say, node equations in terms of node voltages. Okay. So important thing is, we are not writing arbitrary node or KCL equations, but we want to use node voltages in our equations. So what's the meaning of this? Well, you are selecting one node as a ground, and then this is Vs of t. Let me erase this, not to get confused. This is Ea of t, and this is Eb of t, and so on. Okay? So I have, other than ground, 1, 2, 3 nodes. 2 nodes are at unknown potentials. So my goal is writing node equations in terms of these unknown node voltages. Again, the philosophy is very clear. Now, if I know these node voltages, these two, then I know the node voltages, meaning that also the branch voltages, because every branch is in between 2 nodes. For example, this one is in between A and B. This one is in between source and this. Okay? So I can find the potential difference of the nodes. This gives me branch voltage. This gives me branch voltage, their difference like that. So if you know this node voltages, you can find branch voltages. From the branch voltages, you can find branch currents by component equations, resistor, capacitor, etc. And you know everything. You know branch voltages, branch currents across all of the circuit. Okay? Very good. So let's see. I'll be writing KCL at, let's say, A. So this will be obviously A, let's say. Okay. So how can I write this? Minus I1 plus I2 EA minus EB divided by 1 is equal to 0. So what's KCL? So we are writing KCL for the currents going out. This is our simple convention. this EAEB. Again, I'm very happy with this term because I see node voltages present over here. So I'm not happy with I1, I2 terms because these are some other unknowns of this problem. They are, inductor current number 1 and inductor number current 2. And this is my KCL, which is supposed to be satisfied, left-hand side, right-hand side, for all t. These are all t-dependent functions, unknown functions. So how can I express I1 and I2? Well, one thing, again, mutual inductor. So if I again use this red V1, V2 potential differences to represent the mutual inductor voltages, so I'm allowed to use this equation, then how can I find I1 and I2? So let me try to do it from here then. So let's take this matrix. So I'm interested in finding this part and this part. Let's take the inverse of this matrix. I1 of t, I2 of t. Now inverse of this matrix is needed. And you multiply by V1, V2. So why am I doing this? Because I want to express I2 minus I1 in terms of voltages, and this looks good. I'm using the component equation to express these currents in terms of voltages. Of course, there is derivative, but I should be integrating at the end. So what is the inverse of this matrix? So let me write it over here then. This is exchange, alter the sign. And you have 1 over delta. What is this 1 over delta? 14 minus 9. It is 5. Okay. So I have found this matrix as such. So what should I do? Well, I need not the derivative. So I have found the derivative of these I1 and I2. It is this matrix times V1 of t times V2 of t. But I want to integrate this. Okay. So how can I do this integration? Now let's be, again, the operator is this. The inverse operator is, it's our 0 minus to t integral. Okay. So how can I, handle this? So I will do the following. Well, how about this? D times d inverse of f of t. So can I calculate this? So you may say that these two cancel each other and you get f of t back. It looks like a good plan, but let's try to show this. So how about this part? This one is 0 minus to t integral of f of, the variable is tau right now, d tau. Okay. So this is essentially calculating the area, this integral, under this function from this point up to t. So if you change t, area value changes. Now, this is the derivative, isn't it? I need the derivative of this. So this thing in calculus, capital F is the antiderivative. I have this. This is called antiderivative. For example, if this is a function of tau, let's say tau square, then this is tau cube over 3. This is substitution because it's a definite integral, upper limit and lower limit is fixed. So you have this. Okay. So if you take the derivative, well, derivative of this capital F, you get small f. Good news. Okay. Indeed, there was a cancellation. I get that. So this is good. How about the other one? Actually, do we need this one? We need d inverse d, isn't it? We don't need this one, unfortunately. So let me have this then, d inverse d f of t. So what is this? Is it again f of t? Do we have, a similar cancellation? So let's see. Actually, this is a little bit simpler because this is, according to our notation, f dot of t. So this is then integral of 0 minus to t, f dot of tau d tau. But what do I get? I get f of t minus f of 0 minus. Actually, I don't get this one, okay, f of t, because as you see, this is a definite integral. So if you do this, then you are getting not this one, but this one at 0 minus. So this is our result. Okay? So we should be a little bit careful. We should be a little bit careful. There is no always a cancellation between d inverse and d operators. Okay? So we have this case and that case. You should be a little bit careful. Okay. Now, I want to erase this part. Let's also erase this. Okay. Okay, now I have these two results that I have derived. So what should I do? If you wish, I can write here d. If you wish, I can write here d. Okay. So again, these are two equations, equation number 1, equation number 2. I'll be applying d inverse operator, meaning that I'll be integrating equation number 1 from 0 minus to t. Okay. So if I do that, I should integrate this part. Am I right? So what do I get? So d inverse d I1. So I1 of t minus I1 0 minus I2 of t minus I2 0 minus. So I'm left with this. Okay? Times, I have this matrix 1 over 5, 7 minus 3, minus 3, 2. Okay. Times the d inverse of this. So let me put d inverse v1 of t, v2 of t. Okay. So I need, as you see, I2 minus I1. Okay. So again, I can multiply this by minus 1, 1. I2 minus I1. I can multiply this by minus 1 and 1. So I get this. I2 of t minus I1 of t is equal to, let me put this on the other side then. Okay. So I multiply the first equation by minus 1, second equation by plus 1, and I'm adding everything. Okay. So if you do that, I2, this, I want that. Okay. How about this? Now I have 1 over 5, minus 1, 1. So this row is multiplied by, or you multiply this one by 1, you multiply this one by minus 1 and add them. So you get minus 10 and plus 5. So I have d inverse. Let me use this space a little better. 1 over 5 minus 10, 5, d inverse v1, v2. Let's check. So minus 3, minus 10, 3 plus 2, we have that. Okay. So we are almost done. We have to work. So the main difficulty was in this calculation, this mutual inductor, since it is coupling, to get these currents, I have to be a little bit careful because I need this current difference. And still, what is V1 and what is V2? That is the issue. So let's write this equation. Now I have used this already. Now I can write this as I2 minus I1. So this initial condition 0 minus is given, I2. Well, not to get confused, I will call this I01, I02. Because, it's very easy to confuse that. I01, I02. So this is I02 minus I01 is equal to, this is plus, am I right? Okay, minus 2 d inverse V1 and plus D inverse V2 of t plus EA minus EB is equal to 0. Okay? As a function of time is equal to 0. So this whole thing is up to here. It is this. Is this correct? This minus 2 V1 plus V2. Okay. But again, I need to write, these voltages in terms of node voltages, but it's not a big deal because wherever these voltages are, these are branch voltages. So I should be able to express them in terms of node. So what is V1, for example? Vs minus EA. What is V2? V2 is present over here. This is already EA. Okay. We are done then. So let's erase this. So after one more substitution, this will be all done. So if I write this one more time, so what is the coefficient of this? Minus 2 plus, this is 3. Okay, there should be a Vs somewhere. Since Vs is forcing term, it's known, I want to move it to the right hand side. So 2D inverse, just to show it like this. So I want to move these two, these are also known. These are the forcing terms due to initial conditions essentially. So right hand side is this, and let's erase these two. Okay, so this becomes my first equation. So my first equation, first node equation becomes this. Is everything correct? This is minus 2, this is this, EA minus E, EB, and okay, it seems fine up to this point. So let's see, KCL at B. Again, I have two unknowns, so I need two equations. And you'll see that this will be an integral differential equation because there is the inverse already appearing over here. KCL at, well, not actually, because this is a known function. So this known function's integral is something known, this is another forcing term. But due to this actually, due to this we have integral differential equation. Well, KCL at B. Well, so let's check this. So again, I think we can write this somewhat easily. Plus, what is this current going this way? Okay. So that is IC. So this is 3 over 2. Right now we are more, familiar. EB dot is equal to 0. Okay. So this is IC of t. Again, this is supposed to be valid for all t greater than 0. So let's again write this in matrix form then. This is our second equation. EA, EB. Okay, so first equation, coefficient of this, 3D inverse plus 1. I have minus 1. Okay. What else? 2D inverse Vs of t. And I have this initial condition IO1 minus IO2 over here. Okay. The second, EB minus EA and 3 over 2 EB dot is equal to 0. So this becomes my integral differential equation one more time. Integral differential equation. So let's check this. Okay. I think it is correct. Again, the solution of this is, so how do you find the natural frequencies? Instead of d, you are writing lambda, so this becomes 1 over lambda, this becomes lambda, and you try to evaluate the determinant of this matrix as a function of lambda, so you get a polynomial in lambda, so you are trying to make this matrix singular at a specific lambda value, and those lambda values will be the natural frequencies of the circuit. Again, you may miss a natural frequency. Well, we can give it a try. You may miss a natural frequency if it is present at lambda is equal to 0, because we have the handicap of, as you see, this term, integral term. Okay. So again, let me call this, for the sake of simplicity, m of d. Okay. So let me say natural frequency calculation. Natural frequency. M of lambda determinant should be equal to 0. So what is that one? 3 over lambda plus 1 minus 1 plus 3 over 2 lambda. So I have this determinant is equal to 0. It should be equal to 0 at a specific lambda value. Right, actually we know the results, but okay, let's give it a try. Okay. So this determinant is this is minus 1. Okay. So what do I have? Well, if I check this, I get 1 minus 1. So I get a 0 over here. So I get this term as 3 over 2 lambda. Okay. And I have plus 9 over 2. Is this correct? 3 over 2, 9 over 2, plus 1, and 3 over 2 lambda. Let's count it one more time. So I should have how many terms? 4 terms over here, 5 terms. Okay? But the terms without any lambdas, they cancel each other. I should have 3 terms at the end. Do you see 3 over lambda? It's present. Do you see this one? 9 over 2, it's present. And 3 over 2 lambda, that's also present. Okay. So if I then equate it, how should I write this? Let's go this way. Okay. So this becomes divided by 2 lambda, 3 lambda square, plus 9 lambda plus 3. Okay. Or let me put this 3 over here. Lambda square plus this is equal to 6. Am I making a mistake? So I'm multiplying by this. This is equal to 2 then. Okay. Lambda square. Let's check. 3 over 2 lambda square plus 9 over 2 plus 3 over lambda. Okay. Then, again, we would like to equate this to 0. Okay. This should be equal to 0. Equal to 0, 0, when lambda is equal, when the numerator is equal to minus 1 and minus 2. So no surprises, we get the natural frequency that we have expected, but again, we didn't observe the natural frequency at 0. So the word observe is sometimes very technical. Okay. So these are the voltages, branch voltages of this inductor and branch voltage of this capacitor. So if you think about it, in this formulation, this branch voltages, we do not observe this lambda is equal to 0. So one of these modes is not observed. Lambda is equal to 0 is not observed, it's not present for that output variable, for that branch. But we are sure that, because if you think about, we have discussed it before, it's a possibility that there can be some current oscillating over here, okay, at steady state, let's say. So let's say I have a DC input. So there can be at the end a DC current oscillating over here at t is equal to infinity, and this current is equal to 0, this voltage is equal to 0, this voltage is equal to 0, all voltages are equal to 0. So this mode of the circuit may not be visible from the voltage viewpoint, because as you see, voltages are equal to 0, but currents are non-zero. So again, these are like somewhat like more systematic and detailed topics. They require more analysis, but for our purposes, expressing these circuits in this integral differential form is more than sufficient. So why are we discussing these special cases with lambda is equal to 0? Do not get surprised. If, for example, you see on the two modes, for a third order circuit, the suspect is lambda is equal to 0 mode is not present, is not observable. Okay? So that is the case. The same story repeats. So as you can imagine, all of these troubles with lambda is equal to 0 mode, well, it's like a minor issue, but I mean, in practice, you won't be facing this because there will be resistors all around. But in any case, for the sake of analysis, so you are not observing one of the modes because of this 1 over lambda terms, because it's an integral differential equation. Now, one last topic, we will be discussing modified node analysis, and you will see with the modified node analysis we won't be having any integral terms, and it's almost like state equation system, but it's much easier to handle, much easier to, I should say not handle, but much easier to write the formulation. So let me use this part, modified node analysis, let's say formulation. So I'll be just giving you some steps. Introduce auxiliary variables for inductor currents. I will explain this on the same example. Number 2. Introduce current for the ideal transformer primary / secondary currents, auxiliary currents, I should say. Okay, so we are introducing auxiliary unknowns. These are the variables, unknown variables. This, if necessary, introduce currents for the current of voltage sources. So again, these are auxiliary currents. For write KCL equations at nodes. I think we are experts in that. Number 5, write terminal equations for the introduced variables and get, let me write over here, and get an n by n equation system. Okay. So this is supposed to be node analysis alike, isn't it? Because it says modified node analysis, and the word modified applies to this, as I have said, auxiliary definitions. So again, modified, I'll try to apply that. Node analysis. We shorthand form, we write this like M&A, modified node analysis. Okay. So let's try to apply this. Introduce auxiliary variables for inductors currents. So what are my variables? I have two inductor currents. They can be coupled doesn't matter. So I1, I2. Okay. So coupling means this number is equal to non-zero quantity. If they are uncoupled, this number is equal to 0. That's, for me, that's the way it is. So my variables are now I1, I2, because I have introduced two auxiliary variables. Introduce auxiliary currents for the ideal transformers, primary and secondary currents. But there is no ideal transformer over here, nothing to do. Introduce currents, if necessary, for the current of this voltage source, but I mean, it's already, I think, very clear. This is I1, so I don't want to have any new equation. Write KCL at the nodes. Oh, we are done. Okay. Now, what are my node voltages? Like you see, I have EA, EB, so my unknowns are this. These are my unknowns. So these are auxiliary unknowns. And these are node analysis unknowns. I think we are clear on this. Now, how can I write this? So let me write a big matrix then. This is not good also. Okay. What are my unknowns? I1 of t, I2 of t, EA of t, EB of t, and that is it. Okay, so I need 3 separator lines, 1, 2, 3, 4 columns for this. So I will be having a 4x4 equation system, 3 separator lines for the rows. So I have this, 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 something like that. Okay, so what's my first equation? So write KCL equations at the nodes. Okay, let me write this KCL equation. KCL at A. Okay, the first one. So how can I write this? Minus I1. I1 is present right now. Plus I2. So please remember, previously in the node analysis, I had to work so much for this. Because I need to find I1 and I2. I have taken the inverse of this matrix, integrated, get rid of this derivative terms and so on. But right now in the KCL part, now I have 4 unknowns instead of 2. So I can directly write minus I1 plus I2 plus EA minus EB divided by 1 is equal to 0. Okay? Am I right? That is it. That's KCL at A. Okay, it was quite easy. KCL at B. This is EB minus EA divided by 1. EB minus EA divided by 1, and then plus 3 over 2 derivative of VC. But VC is EB, so 3 over 2, so this is not present, sorry, D. So let me make this bigger then. Okay. Is this correct? 3 over 2 EB. Okay, second equation is done. But it says we are done with KCLs. Write terminal equations for the introduced variables. So what do I mean by that? Terminal equations for the well, these are the auxiliary variables. Okay. So actually that is this, mutual inductor. So I need to write the equations for the mutual inductor. So how can I write this? 2D I1 3dI2 is equal to V1. But what is V1? Well, V1 is not an unknown. Okay. So V1 is, well, we are going back, Vs minus Ea. Okay. So let's move this Ea to the other side. Plus Ea is equal to 0. This is equal to Vs of t. Am I right? 2di1, 3di2, 2di1, 3di2, plus EA, 0IB is equal to VS, Okay, we are done with this one also. So how about this second equation? 3d I1, 7d I2, okay. And what is V2? V2 is over here, okay. V2 is just EA, okay. So I should move this to the other side because I'm putting all the known things over here. Minus 1, 0, I'm done. So as you see, again I get a matrix differential equation, but this is indeed a differential equation. Okay, so I have this unknown vector is equal to, yes. So it's almost like state equation because there is no D inverse operators involved, as you see. But it is not a state equation because, as we have discussed many times, this is a third order circuit and I have 4 equations over here. Furthermore, it's not in the structure of, it's not in the structure of state equation structure. But this example is almost like state equation because I1, I2, they're also state variables. VC is state variable. So VC is equal to EB. So these 3 are already state variables. So it was very easy to write this equation because I have introduced essentially, in addition to the state variables, EA. Okay, EA is, as you see, nothing particularly specific. This is just not a state variable and so on. But this makes our formulation of this circuit extremely easy. And since there is no D inverse operators involved, again, if you want to find the natural frequencies, well, I have discussed this already maybe third or the fourth time. The natural frequencies is this matrix lambda. Let's use a little bit of mathematics, such that this m lambda is equal to 0. Okay? So these are our natural frequencies. This is the set for which this equation, m lambda determinant equation, is satisfied. Okay? So again, this is called the characteristic equation. Since there is no D inverse in M and A, all natural frequencies are found, like in this example, lambda 0, minus 1, minus 3 are all, in this case, let's say, found, since this is again a differential equation, there is no D inverse term. Since M and A results in a differential equation, not an integral differential equation. Okay, so this is something very convenient. For example, instead of D, if you write lambda, so I have, let me mark this D. Okay. It's a little bit, can be confusing because it's a 4x4 matrix, but this determinant will be a third order determinant. Okay. Because essentially there is no D on this row. That's just because of it. Third order determinant. So can you see, for example, lambda is equal to 0 is making this matrix singular. It should be making this. So remember, we are replacing these by lambdas. And then that lambda is replaced by 0. So I have D replaced by 0. So I have 0, 0, 1, 0, 0, minus 1, 0, 0. So clearly, if I substitute D by 0, this third and the fourth row, they are becoming dependent because they are negatives of each other. So you see that. For the other ones, I mean, it's not very clearly observed, but clearly we see that lambda is equal to 0. This mode is, it has been found, that natural frequency is found over here. Again, the general solution is always the same. You are looking for the vectors. For example, if this is my unknown vector, you are looking, well, let me call this V. Vh of t is, well, let me write k1 f1 e to the lambda 1t plus k2 f2 e to the lambda 2t k3 f3 e to the lambda 3t. And what are these f? Fk is, you can write this like this, is an element of, let's use somewhat more mathematics, m lambda kf m lambda k, null space of this. Well, as you see, there is very nice mathematics behind this. So what is the meaning of this? Fk is this vector. Okay. So, of course, this is the same type of formulation that we have seen earlier in the state equation system. Over that one, that was, you know, the eigenvector. So this is not the eigenvector because this is not the A matrix, obviously. I mean, its dimension is also different from A. This is a 4x4 matrix. So what is going on? Again, there is nothing new. This sentence tells you that now you have m lambda k values making this determinant singular. Okay, those are the natural frequencies. Then you are making a guess. You are saying that my solution vector, homogeneous part is a, b, c, d e to the lambda t. Okay, again you substitute it over here. Insert into differential equation. Then you get, let's see one of them, m lambda k a, b, c, d is equal to, at the end, 0, 0, 0, 0. Again, making it time independent, cancelling this exponential, all of that story. But what we see is that now this is a singular matrix, or lambda k value, specific lambda k value, one of these, okay, natural frequencies, making this matrix, when substituted, these are substituted by lambda k's, it becomes a singular matrix, meaning that this is a non-trivial null space. So I'm talking about this vector, a, b, c, d vector is this fk vector is over here. In the state equation, this M matrix becomes lambda k minus identity. In the state equation, let me say it that, and we are done. Remember, in state equation system, we have x dot of t is equal to a times x of t plus bs of t, or I can write this as d times x of t. Okay, so this becomes this part, d identity minus a x of t is equal to b vs of t. So state equation has a very specific M matrix, as you see. Okay, let me call this M state equation system. So very specific. For this one, there is no structure, modified node analysis, because it contains a coupled inductor, things like that. So as you see, if you substitute these by lambdas, you get lambda I minus a eigenvalues, null spaces, eigenvectors. It's the same story, but for the state equation, I have a very specific m of d. Okay. Okay, that's all for today. Again, our focus is state equations, but we would like to understand how this formulation goes for other analysis methods also, classical analysis methods, such as node equation, mesh equation, and we have a new analysis method, modified node analysis. Okay, see you next time.